In this example, we are going to find the fourth degree Taylor polynomial for the function natural log of x, and it's going to be centered at 3.8. Here is the Taylor series, and because we want a fourth degree polynomial, the n's are going to go from n is equal to 0 to 4. So this n right here, when we look at the Taylor series, isn't an exponent. It tells us the derivative. So if, for example, if n was 3, that means the third derivative of f. And then, of course, this is our 3 factorial. And then this will be the factor of our term that tells us the degree of the term. So we have to work this out from 0 to 4. So when I plug in 0, 0 comes up here, so we have no derivatives. So we're just going to evaluate the function at 3.8. So I have f of 3.8 here. Then when I plug in 0 factorial, that's down here. And then when I plug in 0 here, this factor becomes 1. And you know that this times 1 is still the same thing, so we don't need to add it in. Now when I go and plug in n is 1, so 1 here, so that means I'm going to find the first derivative and evaluate it at 3.8. So that means I'm going to take the first derivative, evaluate it at 3.8, and divide by 1 factorial. And then we'll have the factor x minus 3.8 raised to the first power. Notice that this is the part of the term that's going to tell us the degree of the term. This part here is going to give us the coefficient. I go through that process and continue from 2 on to 4, and this is what we get after we plug in everything from n is equal to 0 to 4. Now, we need to find for each of these terms so that we can set up our Taylor polynomial. We need to find the values of the factorials, and then we need to find what the derivatives are. Because we don't have x minus 3.8 raised to some power, we just have a 1 there. This is our constant. So this is just going to be the natural log of 3.8 because this tells us to evaluate the function at 3.8 and then divide by 0 factorial since we're plugging in 0 for this first term. So when we plug in 3.8 into the function, we get the natural log of 3.8, and 0 factorial is 1. So we would just have a 1 under here, which we don't need to write in. So for the next term, we're going to take the first derivative, evaluated at 3.8, and then we'll have x minus 3.8 to the first power, and then we divide by 1 factorial. Since 1 factorial is 1, then nothing on the bottom is going to change. But when we find the derivative of the natural log of x and evaluate it at 3.8, since the first derivative is going to be 1 over x, and then we plug in 3.8, this is going to be our coefficient for the second term. So I have 1 over 3.8 here. And then we just repeat that pattern. And so what we end up having at the end is this whole thing right here. 2 factorial is 2, so that's going to go here. 3 factorial is 6, so that's going to go here. And then 4 factorial is 24, so that's going to go here. Of course, you can reduce this and make it 1/3 because you have 2 over 6 here. And of course, you can make this 1/4 and reduce that 6 over 24. Now, if you look at the picture that I created here so that you can visualize what's going on here, in the black, you have your natural logarithm function right here in the black. And then when I graph this fourth degree Taylor polynomial, this is what I get right here. Okay, I'm zoomed into that area so that we can take a look at it. The center is 3.8. So here's the point right here where x is equal to 3.8. If we look really close around the area of 3.8, these two functions are very, very close. So if you're in the vicinity of x equals 3.8, we can use the Taylor polynomial to evaluate an approximation for the natural log of x. So if we're near the value x equals 3.8, if we're in this neighborhood, you can see that the Taylor polynomial would make a very good approximation for the natural log of x.